In this lecture, we will explore how rich and large the class of measurable functions is, by, for example, showing that it is robust under all sorts of limits. Then, paradoxically, we will use that robustness to show that under limited information, the class of appropriately measurable functions is very small and limited as well. Last time, we showed that measurable functions are closed under composition. In particular, we showed that if f is a Borel measurable function and x1 through xd are Borel random variables, that is, they are measurable maps from a probability space into the Borel sigma field, then the composition is again a Borel random variable. And we use this in the special case where f is a continuous map because continuous maps are, in fact, Borel functions. One important example where that will be used today and over again in the future is applying to the positive and negative parts of a function. Given two numbers x and y, the function which takes the pair to the maximum, which is also denoted x vy, and the minimum, which is also denoted x wedge y, are of course continuous functions of two variables. And that means, following this result here, that the positive part of a random variable, which is its maximum with 0, and the negative part, which is the negative of its minimum with 0, are measurable. These are non-negative measurable functions, and we can reconstitute the original function x as x plus minus x minus. And from that, we can also conclude that x is measurable if and only if its positive and negative parts are both measurable. And by the way, notice that we also have the absolute value of x, which is x plus x minus, and therefore it is also measurable if x is measurable. Now, we could get that directly by noting that the absolute value function is a continuous function on the real line and applying this theorem again there. But this theorem is useful not just in the case of continuous functions. Often we will apply it to discontinuous functions that are nevertheless Borel measurable. For example, here, the function 1 over x on the reals is not a continuous function. It's not even defined at 0. But we can define it to take any value we like at 0, like this. Let's let it take value alpha at 0. Then this is a well-defined function, but no matter what choice of alpha we make, it's not a continuous function. However, it turns out that it is a Borel measurable function, no matter what choice of alpha we make. Let's see why. For starters, let's take alpha equal to 0. That will make this argument simplest to start. Then, we need to check that the preimage of any Borel set is a Borel set. But as we saw, it's good enough to check that the preimage of any appropriate kind of interval is a Borel set. So let's do that. Let's look at I alpha with alpha equal to 0, preimage on the interval from x up to infinity. Now, what that preimage looks like is going to depend on whether x is positive or negative. If x is positive, then this is just the interval from 0 up to 1 over x. And notice that x is included there because the interval open from 0 up to infinity is indeed the image of the open interval from 0 up to 1 over 0, which is infinity. On the other hand, if x is less than 0, well then, by our definition of the function I alpha with alpha equal to 0, 0 is included in the preimage, as is the entire positive real line, since the entire positive real line is included here, but we also get the interval from minus infinity up to 1 over x. And there is a complete description of the preimage of this map on any such interval, and we note that all of those are either one open interval or a union of a half open interval and an open interval, and those are all Borel sets. So this is a Borel set for any x. And we conclude from there that I0 is Borel measurable. Now, what about I alpha? Well, in general, I alpha, the function which is 1 over x except taking value alpha at 0, can be written as I0 everywhere but 0. So let's multiply that by the indicator of the set excluding 0, plus alpha times the indicator of 0. That's the definition. It's equal to 1 over x except at 0, which is what I0 is equal to, and equal to alpha at 0. Now notice that this is constructed from measurable functions. Indicator functions of measurable sets are measurable, together with I0 that we know is measurable, and a constant which is measurable, by addition and multiplication, which are continuous operations, and therefore the whole deal is measurable. And that shows that this function is measurable in general. Now, how is that useful to us? Well, if I have a general function f from omega to r, which is Borel measurable, then its composition with this measurable Borel function is measurable as well. And that function is 1 over f at x, provided that you can do that reciprocal when f at x is not 0, and alpha if f at x equals 0. So that function, which could be quite complicated, the set where f at x equals 0 could be a dense set, for example, that function, which is definitely not continuous in general, is Borel measurable. Now let's take a look at how measurable functions behave under limits. It turns out that measurable functions play very well with limits, which is something that is not true for continuous functions. If fn is a sequence of Borel measurable real-valued functions on a measurable space, for example, random variables on a probability space, then their supremum, their infimum, their lim sup, and their lim inf are all measurable functions. And that means in particular that if fn has a pointwise limit, then it also will be measurable since it will be equal to either one of those. Now let me make two comments. The first is that all of this is very false for the class of continuous functions. Continuous functions are not closed under supremum, infimum, lim sup, or lim inf. One can take sequences of functions as smooth as you like, and by taking these operations produce functions that are nowhere continuous. Measurable functions form a much more robust class than continuous functions. The second comment I want to make is that as this is stated, it is not strictly true. And the reason is that we have written this to consider functions taking only real values. And the problem is that a sequence of measurable, even constant functions could have infinite supremum or negative infinite infimum, and similarly for their lim sup and lim inf. So to make this totally precise, we would need to consider here functions that take values in the extended reals. That means the reals together with plus and minus infinity, where we define infinity times any non-zero number to be either plus or minus infinity, depending on how the signs match, and plus or minus infinity times 0 to be 0 no matter what. One can quickly develop this extension of the reals and the Borel sigma field, making the symbols move the way they have to. We're going to play a little fast and loose here and ignore all of those intricacies, but simply note that the theorem without the extended reals here is 100% accurate, and the proof 100% correct that we're about to give, provided that one makes the additional assumption that these quantities are finite. And that's the only case where we'll need this proposition, at least in this lecture. So, why are these quantities, supremum, infimum, lim sup, lim inf, of any sequence of measurable functions also measurable? Well, we just go to the definition and check that the preimage of any such limit function maps Borel sets to Borel sets, or as usual, maps appropriate intervals to Borel sets, which is good enough. So, for example, let's take the supremum of a sequence of measurable functions. What does the preimage of that supremum do to a half-open interval from -infinity up to t closed? Well, by definition, that is just the set of real numbers x for which that supremum takes value in that interval, meaning that it is less than or equal to t. So that is to say, it's the set of all real numbers x. Well, how can the supremum of a sequence be less than or equal to t? The supremum is the least upper bound, and for the supremum to be less than or equal to something, for the least upper bound to be smaller than or equal to t, that means that t must be an upper bound in particular. So that means that fn of x is less than or equal to t for every n. But that's just another way of saying that this is the intersection over all n of the set where fn is less than or equal to t, or in other words, the intersection over all n of the preimage of fn on the interval from -infinity up to t. Now, the interval from -infinity up to t is a Borel set, and each fn is assumed to be Borel measurable. Therefore, each of these sets is Borel measurable, and therefore the intersection of all of them, since it's countable, is Borel measurable. Great, so now we know the supremum of any sequence of Borel measurable functions is Borel measurable. What about the infimum? You just do exactly the same thing, but to make things easy, we'll consider this kind of interval instead. And I'll leave the details to you. Now, what about lim sup and lim inf? Well, here we just remember the definition. The lim sup of a sequence of functions is the infimum over n of the supremum of the functions for all j greater than or equal to n. Well, all of the fj's are measurable, and so the sequence fn, fn plus 1, fn plus 2, and so on is a sequence of measurable maps, and therefore, by what we just proved, its supremum is measurable. So for each n, this is a measurable map, and we have a new sequence of measurable functions. And so therefore, by what we stated how to prove here, its infimum is also measurable. And so by just applying the two cases above, we see that the lim sup is also measurable, and the lim inf works exactly the same way. Thus, not only are measurable functions robust under all kinds of limits, but the proof that they are is exceedingly simple. Now, speaking of exceedingly simple, let's talk about simple functions. These are going to be our bread and butter for approximating measurable functions. A real valued function on any space is called simple if it has finite image. That is, if the image of phi on the whole domain is a finite set. For example, we could take any indicator function or any scaled indicator function. Indicator functions are simple because they take only two values, 0 and alpha in this case. And remember, by the way, that such an indicator function or scaled indicator function is measurable if and only if the set that it indicates is measurable in the sigma field that we're interested in placing on the domain. So here's a picture just to demonstrate. In this case, the domain A is a union of a half-open interval and 2 points. And so here's the graph of that simple measurable function. It takes values alpha or 0, depending where it is. Now, in general, simple functions actually have a form just like this, except it's going to be a finite sum of those terms. See, if phi is a simple function, then its image, phi on omega, is a finite set. Let's call that set alpha j, where j ranges from 1 up to some finite n. And let's define aj to be the preimage of phi on the singleton value alpha j. Well then, we can rewrite phi, the entire function, simply as the sum, j going from 1 up to n, of alpha j times the indicator function of aj. Indeed, this just says that phi takes the value alpha j on the set aj, which is exactly what this says here. And note, by the way, that these aj's are disjoint, because the alpha j's are assumed to be different numbers. Well, just like a single indicator function is measurable if and only if the set it indicates is measurable, it is easy to check, although slightly longer to write, that such a simple function is measurable if and only if each of these sets in the partition that it indicates are measurable. And so that's what a simple measurable function is. It's a function each of whose preimages on every real number is a measurable set in the domain sigma field. Now, notice writing it this way, it looks like this is a very difficult condition because we have to check it for all real numbers, but it's important to note that this is equal to the empty set for all but finitely many alpha, which is why in this simple case of a simple function, we can check this condition only and not have to worry about the preimage on anything but singleton sets. So to be clear, this says the same thing as the sum j going from 1 up to n of alpha j indicator of aj, where these are disjoint, is measurable if and only if all of those sets, a1 through an, are measurable sets. Now, what's the big deal about these simple functions? Other than them being simple and easy to compute with, why would we want to? The reason is that all measurable functions can be really well approximated by simple functions. And here's the theorem. Let f be any measurable Borel function. That is, it's defined on some measurable space, takes values in the reals equipped with the Borel sigma field, and is f be measurable. In that case, we can always find a sequence, phi n, of measurable functions whose limit is that function. And if you're wondering what kind of limit it is, it's actually uniform if we restrict to the set where the preimage is bounded. That is, if we restrict to those x for which f at x is less than or equal to some big real number m in absolute value, then on that set, this is uniform convergence. And so in particular, by taking m larger and larger, we certainly get pointwise convergence. So why is this true? It sounds like a very challenging thing to prove, but it's not. And this picture shows how to do it. We can do it in a systematic way, which is what we've done here. What we do is we divide up the range. We take the range of the function and chop it into small pieces, and then approximate the function by a locally constant function corresponding to that partition of the range. Now, to make things a little bit easier, let's start by considering only non-negative valued measurable functions. It's actually sufficient to consider those, because if we can prove this theorem for those, then afterward we can apply the theorem to the positive and negative parts of f. If I can approximate f plus by some sequence phi n plus and f minus by some other sequence phi n minus, then f plus minus f minus will be approximated by phi n plus minus phi n minus, which is easy to show. And so we'll just consider the positive case. In that setting, we can be very systematic about this and always divide up the range dyadically. And on each horizontal bar, I'm going to approximate the function on that entire set by its value at the bottom. That's what this does. This picture takes this complicated looking function and does this lower flattening approximation in the case n equals 2. We've divided up the range into quarters and then approximated the function from below by those values. And here's an exact formula for it. And just to be clear, these sets here are the preimages of f on intervals from k over 2 to the n up to k plus 1 over 2 to the n. And once we get all the way to the big value, not 1 over 2 to the n, but 2 to the n, we stop there. If the function continues to grow above some large height, then we cut it off flat after that, which is not a very good approximation of the function on that set where it's large, but that's okay because we'll get closer to that part in the next iteration, phi n plus 1, which goes twice as high. It is very easy to check from the definition, or just from pictures like this, that phi n is less than or equal to phi n plus 1. If I subdivide the range in half, then on half of the range, the function's approximate value is going to stay the same, but on the other half, it may go up. It certainly cannot go down. But we're always approximating from below. We're looking at the values from below the function, okay? Just because we look on the interval where f takes values above k over 2 to the n and approximate it by k over 2 to the n there. And so we get that this is always less than or equal to f. So in particular, this is an increasing sequence, and it's bounded by this finite function f above, and therefore it converges at each point to something. And what is the something that it converges to? Well, by construction, if I look at f at x minus phi n of x, that's going to be non-negative, as we've written right here, but it's also less than or equal to 2 to the minus n, which is the width of this range interval. Now this holds true on the set where f is less than or equal to 2 to the n. And so on that set, we get that phi n converges to f uniformly, which proves the claim. The only thing we need to make sure here is that these functions, phi n, which are simple functions, are actually measurable. That means we just need to check that these sets are measurable, but that just follows from the measurability of f and the fact that these half-open intervals are Borel sets. And so that proves this robust approximation theorem. We're going to use this simple function approximation, and in particular, this picture, an idea of subdividing the range of the function, as our key starting point when we define the Lebesgue integral in the next lectures. But before we head in that direction, I wanted to now show you how to use this incredible robustness under limits and approximation by simple functions to prove that measurable functions, when we have limited information in the measure space in the domain, is a very restricted class. And here's the result. Remember, we began this lecture by recalling that if I have a sequence of d random variables, measurable maps, and a Borel measurable function, then the composition f at x1 through xd is measurable. Of course, not every fb measurable function looks like this for these particular random variables. But what if we replace f? What if we don't have this big sigma field in the domain, and the domain sigma field is instead the sigma field generated by these particular random variables? The result is exactly that these are the only measurable functions in that case. So to be precise, suppose I have a sequence of random variables that are Borel measurable with respect to whatever sigma field we start with in the domain, and then we restrict our attention to the sigma subfield of f generated by x1 through xd. Then if y is any random variable measurable with respect to that sigma field, it does look like this. It is just a Borel function of x1 through xd. Now this result is sometimes known as the Dubin representation theorem. We will use it all over the place, and every probability textbook uses it very frequently, often without stating that it's being used. This is one of the key points that I was most confused about when I took probability theory 20 years ago from Dubin. I guess because the theorem is named after him, he thought it was too simple to even mention to us. But I'm making sure to mention it to you, and we're going to prove it now. To see why this is true, we need to recast this object, the sigma field generated by a collection of random variables. Remember, by definition, that's just the smallest sigma field over the domain space, with respect to which each of those random variables are measurable as Borel functions. So we could write that then as just the sigma field generated by the preimages under each of the xj's of the Borel sigma field. But there's an easier way to write it for our purposes, which is as follows. Let's define block x to be the random vector, the vector-valued function, whose components are x1 through xd. This is a function from omega into Rd. Then the sigma field generated by x1 through xd is the same thing as the pullback under this vector map x of the Borel sigma field over Rd. And remember, that just means that it is nothing other than the set of all preimages of Borel sets under the map X. That is because there's a nice connection between Borel sets over Rd and Borel sets over the reals. This is a nice product structure, which we've seen before, and proving this is on your homework. Once we have that nice invariant characterization in hand, we can prove the Dubin representation quite easily. So, to begin, let's prove it in the special case where that function y is an indicator function. It's the simplest of all simple functions. Well, if it's an indicator function and it is measurable with respect to this sigma field, then we know what that means. That means that this set A must be in that sigma field. By the lemma that we just stated on the last slide, that sigma field is the pullback of the Borel sigma field, which is exactly to say that this A must equal x inverse of B for some Borel set B over Rd. Well, that means that 1A is the indicator of x inverse of B. And here's the trick. We note that the indicator function of the preimage of B can be written instead as the indicator function of B composed with x. You just have to check that both of these say the same thing. On this side, we take any point in omega, we map it to x of omega, which is now an arbitrary point in the image of x, and we decide whether that point in the image of x is in B or not. Now over here, we're starting with a point in omega and checking to see whether it is in the image of B or not. So these give the same value. So in this special case, we have indeed checked that y is the composition of x with a Borel measurable function of d variables. So here we can just take f equal to 1b. Great. So what if y is not an indicator function? Well, let's take it one step further, a little more complicated, but still simple. Let's assume that y is an arbitrary, measurable, simple function, which means that it has the form finite sum from 1 up to n of some constants alpha j times the indicator function of some measurable sets aj that are disjoint. Now we're assuming that this is measurable with respect to that sigma field. And so, as before, that means that the aj's are in that sigma field. And so, following exactly the reasoning we just did, that means that these things are pullbacks of Borel sets. So that says that aj is x inverse of some bj, where bj's are Borel sets in d variables. And so that means that we can rewrite this y as the sum of alpha j times the indicator of x inverse of bj, and again, following exactly the same reasoning we did here, we see that that is equal to the sum of alpha j indicator of bj composed with x. And composition like this respects the sum, so this is f at x, where in this case, f is just the simple Borel function given by the sum of alpha j times the indicator of bj. And so we have proved the Dubin representation in the case where the y is a simple function. Okay, now finally, let's assume nothing about y other than what we are told in the corollary. We just want y to be any measurable map from the sigma field generated by x1 through xd, taking values in the reals and being Borel measurable there. Well, by our limit theorem, we can approximate any such map by simple functions uniformly on bounded subsets in the range of the function. So that is to say, in general, we can take a sequence yn of simple functions that are measurable and therefore that look like this, such that yn converges to y, certainly pointwise. And so that means that y is the limit as n goes to infinity of the yns. The limit will be the same as the lim sup, since the limit exists. Now, by what we just proved, each of those yns is equal to some function fn composed with x, where fn is a Borel measurable function of d variables. So what we can do is define f to be the lim sup as n goes to infinity of fn. And then, clearly, this is equal to f composed with x. Now, if we want to be a little persnickety, this could take infinite values, but if we assume that our original y does not take infinite values, this chain of equalities shows that f won't either. And so this concludes the proof. Thus, measurable functions are rich and robust, but under limits of information, that is, if they are measurable only with respect to the information we have about a set of random variables, measurable functions are nothing other than Borel functions of those random variables. The key tool in understanding both sides of this coin is the robustness of measurable functions under limits, and in particular, their easy approximation by simple functions. So we are now going to take that knowledge and figure out how to properly integrate measurable functions in wide generality.